So welcome to lecture 9 of Power System Protection course. In the last lecture, we discussed also overcurrent protection and we'll continue that overcurrent protection. And last class we discussed from the elementary side, the fuse protection. Then we talked about different characteristics of fuse protection. Then we talked about overcurrent relay, different types of overcurrent relay based on the operational aspect, definite time overcurrent relay, then inverse definite time overcurrent relay, then all the characteristics also we have seen in those different standard characteristics, IEC standard characteristics, then IEEE standard characteristics, right? So in this lecture little bit we'll see how we can implement or how we can use this definite time or inverse definite minimum time relay. Let us see how we can implement these relays. Okay, so let us start with implementation of the overcurrent relay using induction disk. First of all, we'll see a basic electromechanical structure, and from which we'll see how the standard equations are being derived from this electromechanical relay. So this is the structure of the electromechanical relay. You can see here, this is the TMS adjustment dial, right? Okay, so this is your TMS adjustment dial, where by adjusting the TMS we can get the time delay. Okay, and next we can see here, this is one electromagnet where the coil is wrapped and the coil is connected to the relay. So this is connected to relay circuit. Okay, and you can see here IR is your relay current. As soon as the relay current passes through this, then in the electromagnet the flux is produced. Okay, and the electromagnet, one part of the electromagnet is shaded. Here we can see the shaded coil is wrapped around one portion of the electromagnet, and therefore we get get two fluxes having a phase difference. Okay, in phi 1 and phi 2 we can create a phase difference as per our requirement. And here we have a movable contact. This contact is your movable contact, which in fact moves, right? When as soon as it is excited, that means your disk is excited. This is your aluminum disk, right? So as soon as the disk rotates, because of the torque produced on the disk, we'll see how the torque will be produced in the aluminum disk. And as soon as it is produced, this movable contact will come closer to the trip contact and it will short circuit these two trip contacts. Okay, as soon as it is shorted, then it will give signal to the circuit breaker, and there are two springs to provide the restraining force to this contact. As soon as there is no excitation, it will go to its original position because of these two springs. Okay, and here there is a permanent magnet, obviously, right? Okay, so now we'll see how the torque is being produced in this. So let us say the phi 1, that is the flux here, phi 1, right? This phi 1 is, let us say, phi m1 sine omega t, and phi 2 is, as it will create some angle, the phase angle difference between phi 1 and phi 2, so therefore let us say it is phi m2 sine of omega t plus theta. Okay, so there is a phase angle difference between these two fluxes, and that is theta. Okay, so now I can write I phi 1. What is this I phi 1? I phi 1 is the current, the eddy current produced in the disk, aluminum disk, because of these two fluxes. I phi 1 is produced because of the phi 1. It is because of the phi 1. And I phi 2 is produced because of the phi 2. These are the eddy currents produced on the aluminum disk. This is your aluminum disk, right? Aluminum disk. So obviously I phi 1 will be directly proportional to the voltage because of the change in the flux phi 1. So that change in voltage, that is nothing but it will be directly proportional to the d phi 1 by dt, and it is nothing but it is directly proportional to omega phi m1, omega phi m1 cos omega t. Just by taking the derivative of phi 1 we'll get this expression. Then I phi 2 will be directly proportional to d phi 2 by dt, which is nothing but equal to omega phi m2 cos of omega t plus theta. Okay, now we saw that these eddy currents produced in the aluminum disc is directly proportional to omega phi m1 and omega phi m2. Okay. Now we know the force produced on the aluminum disc will be because of the interaction of the flux and the current. So by the interaction of the flux phi 1 and I phi 2, it will be phi 1 I phi 2, which will be directly proportional to phi m1 phi m2 sine of omega t cos of omega t plus theta. And similarly F2 will be equal to phi 2 I phi 1. It is because of the interaction of flux produced due to I phi 2 and I phi 1, and that is directly proportional to phi m1 into phi m2 sine of omega t plus theta into cos omega t. Okay. So these are the two expressions of force, and these two forces will be uh, not exactly opposite to each other, but they will be they are opposing to each other, making some angle, right? So let us find the vector difference between these two forces, F2 and F1. So if we'll find the vector difference between F2 and F1, that is F2 minus F1, it will be directly proportional to phi m1 phi m2 sine of, that is we'll take the uh, difference, then it will become sine omega t plus theta cos omega t minus cos omega t plus theta sine omega t. Okay. Now we'll see that F2 minus F1 will be directly proportional to phi m2 into phi m1, or phi m1 into phi m2 sine theta. If we'll simplify this expression, we'll get sine theta. Okay. So now, so this F2 minus F1 is nothing but that is directly proportional to the torque, induced torque, and therefore I can say the induced torque Ti is directly proportional to I square, because phi m1 and phi m2, if I'll write, I can write it as directly proportional to Im into Im. Okay, so it is Im square, I can write it. So Im square, I can write it, it is directly proportional to root 2 I square. I is nothing but the RMS value of the current, that is the current flowing through the relay coil. Okay, so that is root 2 I square. I can write I square only because Ti, I can write Ti is directly proportional to I square. Okay, then I can write Ti should be greater than Ts plus Td if we want the disc, the aluminum disc to rotate, right? This is your aluminum disc, and this disc will rotate only when your Ti will be greater than Ts plus Td. So this permanent magnet, sometime it is provided to provide the damping as well, and also the damping torque is produced because of the friction and windage losses, right? So therefore I can say, and this Ts is your spring torque. This torque is opposing to the induced torque. It is produced by these two springs that is connected to the spindle, and your damping torque will obviously, it will damp out the torque, and it is obviously the opposing torque of the opposing to the induced torque. Then when the disc is on the verge of deflection, that means verge of deflection means your, as at the point when the exactly when it is about to start rotating, the disc is about to rotate, that is the verge of deflection. Right, at that time I can say that, or we can say that Ti should be equal to Ts plus Td. Ti is your induced torque, Ts is your spring torque, and Td is your damping torque. Okay. So now I can write Ti is directly proportional to I square, so I can write Ki I square minus Ts equal to Kd omega. So I have taken here Ti equal to Ki I square. Okay. So Ki I square minus Ts equal to Kd omega. Now at the verge of deflection, your omega is 0, right? When, or you can say when I equal to Ip, that is at the verge of deflection, your current is at the will be equal to the peak value, right? Not greater than the peak value, it will be equal to the peak value. And your omega will be equal to 0 at that time, and hence substituting these two quantities, I can say that Ts equal to, because here Kd omega will be 0, and substituting I equal to Ip, I can say Ts equal to Ki Ip square. Then substituting this in the original equation here, in this equation, just substituting this in this equation, now what we'll find? We'll find Ts into m square minus 1 equal to Kd omega. So how it is obtained? Just by substituting Ki Ip square in the Ts. Okay. So we'll take common Ts outside, and it will become m square minus 1. M is nothing but I by Ip. Okay, so therefore where m is nothing but it is I by Ip, which is the multiple of peak of current. We know already we have discussed this. That also we call this as plug multiplier setting or plug setting multiplier, right? PSM. Okay, sometimes we call it PSM. So your M will be equal to I by Ip, and theta is the angle or disk rotation. Here Kd into d theta by dt, omega is nothing but equal to d theta by dt. So that is the angle or disk rotation. Okay. So this theta in fact is not equal to this theta. This theta is different. This theta are, this is the theta, this is the phase angle difference between phi 1 and phi 2, and this is in fact the deflection of the aluminum disc. So it is reasonable to ignore the initial acceleration of the disc, since the disc is very light. We know the disc is made up of aluminum and it is very light, and acceleration that acceleration, in fact, it is quickly settles to the final constant velocity, right? So if this simplification is introduced into then we can approximate the above equation as this, right? So we can say that Ts into m square, this we can approximate this equation in fact to this, right? So we can say that d theta by dt is because it very quickly achieves the deflection, so we can assume that uh, theta d theta is theta and dt is t, so I can write it theta by t is nothing but equal to ts by kd into m square minus 1. So then I can write Tp, that is the time required to pick up, that is pickup time, will be Kd theta p, okay, just by taking theta to the right hand side, Kd theta p by Ts 1 by m square minus 1. Okay, now I can write this as constant Kd theta p at Ts, that is, if I'll assume this as constant, I can write T1 by or Ti by m square minus 1. Okay, so when there is large current corresponding to the large value of m, so when there is a large current, what will happen to m? M will be equal to I by Ip, right? So when this current is very large, then obviously m will increase, right? M will drastically increase, right? So that will cause the electromagnet to saturate, and this causes the flux to reach a limiting value, right? So it causes the flux to reach the limiting value, because we know the magnetization curve of any electromagnet that saturates after some time, which produces a constant operating time, right? Then it finally approaches a constant operating time, which we designate, let us designate this as T2, right? So then your equation will become your time for operation, that is pickup time or time for operation, will become equal to T1 or Ti by mp minus 1 plus T2. Okay, so this T2 is your fixed time, right? If we'll see this equation, as your m will become large, right? So as your m is becoming larger, then the denominator will be becoming larger, making this as very small quantity as compared to T2. So finally, if your current is very large, then what happens? The operating time is settling to T2. That means it is becoming a definite time. As we know, the inverse minimum definite time characteristic, right? It will be initially inverse, then it will in the initially it will be, so if we'll plot current characteristic, then initially it will be inverse, sorry, it will be inverse, then in the when the current value will increase, it will be definite, right? So that is inverse minimum definite time current characteristic of relay, right? In fact, this gives that characteristic, inverse minimum definite time. Okay, so now let us see the application of definite time overcurrent relay for protection of a distribution feeder. Okay, so let us see first the application of definite time overcurrent relay. Then we will see the inverse definite time overcurrent relay for protection of a distribution feeder. So let us consider a distribution feeder with a source. The source is not a generating station. This is in fact a substation which is feeding the feeder, this radial distribution feeder, right? And Zs is your source impedance, that is equivalent source impedance, and it is the feeder is having three buses, bus C, bus B, and bus A, and the loads are connected, having load current ILA, ILB, and ILC. And there are two relays connected, relay A and relay B. So obviously if we'll see this structure, what we are thinking, we are thinking that this is a three-phase line and the relays are all definite time over current relay, right? So already we know the characteristic of definite time over current relay, right? And what is the purpose of RB and what is the purpose of RA? The purpose of RB is to protect this section of line, this BC section of line, right, as primary protection, and it provides the primary protection to the section BC, and it provides, the relay A provides primary protection to section AB, right, whereas relay A is providing the backup protection to section BC. That means relay A is providing primary protection to section AB, right? And it provides also backup protection to section BC, right? Okay. So now we can see the fault current, how the fault current varies based on the fault location. If the fault location is here somewhere, we'll get the largest fault current, right? Then gradually as the distance increases, then the fault current gradually decreases, and finally at point C, the fault current will be less, right? Okay. So then we can see here that based on the load current and the fault current, we can adjust these two relays, right? Okay. So given the magnitudes of all the loads and the fault currents, suppose we got the magnitudes of the load currents and the fault currents, right? Then at all the buses, then how we can set the definite time over current relays at bus A and bus B so that the entire feeder gets overcurrent protection arranged as primary and backup protection. So how we'll do it? Let us see. Yeah? So there are a few steps to be followed. The first step is first select the ratios for all the cities. It is very important. We need to select the ratios for the cities. Then the secondary current of the city is decided by the rating of the relay current coil. Okay, the secondary current obviously it is decided based on the rating of the relay current coil. And the third step is the city primary current is decided by the maximum load current to be carried by the city primary. Okay, so city primary current will depend upon the maximum load current what we have, and that will be decided by this maximum load current. Then carry out the relay setting. Relay setting means we have to set the time delay, and that is through the TMS. That means we need to set TMS and also the PSM, that is clock setting multiplier. So this in fact gives us the uh, pickup current, right? So pickup current, and this gives us delay time. And as we know here, this is the definite time relay, so we'll have delay time, a fixed delay time, right? Okay. Then how to select the pickup value of the relays? Let us see how to select and how to set the operating time of the relays. These two parameters are very important to set in the relays. So let us see how to select the pickup value of the relay. The thumb rule says, this is your thumb rule when you are setting the pickup value. Thumb rule is IL max should be less than IP, should be less than IF min. So IL max is your maximum load current, right? So this is your maximum load current, right? And IP is your set, that is the pickup current we need to set and IF min is your minimum fault current. Okay, so minimum fault current and maximum fault current can be decided based on the fault analysis in the network, right? Based on the fault analysis, we can decide the minimum fault current and maximum fault current. In fact, the maximum fault current flows in the network when there is a three-phase fault, a symmetrical three-phase fault, and minimum fault occurs when there is a single line to ground fault or single phase fault, right? Okay, now we can see in fact, the clock setting, how we set, right? So you can see here, this is your load current, actual load current, and this is your permissible load current range. Okay, that is the overloading condition. Now, your minimum fault current is here, and that means we need to set the pickup value between this range, right? So this is your range where we need to set the pickup value, right? And this is your maximum fault current, right? Okay, then how to set the operating time of the relay? Let us see then. So let us say if the fault is cleared, let us say this is your fault instant where the fault is initiated. Okay, so fault instant, we call it fault instant. Then as soon as the fault initiated, let us see at the section BC the fault is initiated, then what will happen, the relay B will instantaneously, it will respond to this, right? So therefore there obviously it will instantly respond, but still there will be certain operating time for relay B, right? So that we call relay RB operating time or TRB. Okay, then after that the relay will give the signal to the circuit breaker B, and obviously it will take some time. The circuit breaker takes some time, and that time we know that time is called circuit breaker operating time, or we call it TCB B. Okay, so then obviously we should keep some overshoot time for relay A to operate, and that overshoot time, in fact this is represented as TOSA, and therefore I can write that relay A operating time is nothing but it should be greater than TRB plus TCBB plus TOSA. That means the operating time of relay A should be greater than the operating time of relay B plus operating time of the circuit breaker associated with relay B plus the overshoot time for relay A. So this overshoot time is required because sometimes the time may mismatch, right? So therefore we keep some overshoot time. So the correct procedure would be to start the setting from the tail end, right? Tail end of the feeder, tail end, at the tail end we have we have relay B, right? Therefore we start the setting from relay B, and the relay which is at the end of the radial feeder can be made to operate without any delay. That means instantaneously it should respond, as it doesn't have to coordinate with any other relay. Okay, so therefore relay B should be instantaneously respond, but still we should there is some operating time, and that time operating time is known as TRB. Okay, so here one example, through the example it is demonstrated. We can see here, this is the example, this is a three-phase line, and the same example we are continuing, and here just some values we have taken here, right? So we have taken TRB, that is the operation time of relay B, we have taken in fact 0.1 second. Okay, so it is instantly operate, but still some time it will take. So let us say that is 0.1 second, and your pickup value for relay B will be set. How it will be set? It should be set between the current. maximum load current at bus C and the minimum fault current at bus C, right? So by that we can set up the pickup value or pickup current in the relay B, and it will be, the time setting will be instantaneous, and that is around zero point 0.1 second. So then how will set relay A? Okay, so this will provide the backup protection to section B and primary protection to section AB, right? So therefore ILB plus ILC will take the load current of LB, the load current at bus B and load current of bus C added together should be less than the pickup current of relay A, and that should be less than the minimum fault current at bus number C. So that means I can say the operating time of, so pickup current will be within this range, and operating time of relay RA will be, should be greater than TRB. In fact, should be greater than TRB plus TCBB TOSA. So that means the operating time of relay B plus operating time of the circuit breaker B associated with relay B and the overshoot time of relay A. So generally the overshoot time is taken as 0.2 and the operating time of circuit breaker around 0.5. So these are the values, standard values, and the operating time of relay B is 0.1. So therefore the operating time of relay A should be set at 0.8 second or greater than equal to 0.8 second. Okay, so this is how we set the, or we coordinate the definite time relays in the distribution feeder. Okay, so now we can see here that same example, right? This is your fault current IFA, how it is varying, right? And your operating time also for relay A. For relay B, it is 0.1 second, it is taken the standard value, and the STI, that is the standard time interval, is 0.7 second, which is nothing but TCB B plus TOSA, right? So this is a standard time interval. We call it standard time interval, or sometime we call it coordination time interval, right? That is known as coordination time interval. And sometime it is also known as standard time interval, STI, right? Standard time interval. Okay, so now we can adding these values, we'll see the operating time of relay A will be 0.8 second minimum, right? So this is your fault location where the fault happening. So we'll demonstrate more. This is your definite time relay coordination. We'll next class, in fact, we'll see the a we'll see the inverse definite minimum time relay, uh, how we can coordinate it, right? So in the lecture number 10, so we'll continue the overcurrent protection. So thank you very much for your kind attention. uh, Thanks a lot.